Hi, and welcome to 2D2, the second video in our two-dimensional projectile motion unit. Um, just quick reminder what we learned in our lab. A projectile has, when we're talking about horizontal motion, it is going at a constant velocity. I'll just put CV for constant velocity. So on a motion map, this looks like dots evenly spaced apart, and these velocity arrows are all look consistently the same. In terms of a graph, well, a position time graph would be like this, and a velocity time graph would look like this. And our mathematical model for this one would look something like, well, the velocity would be equal to delta x over delta t, which is kind of one way we look at it, and or we could say delta x is equal to v times delta t, depending on what we're solving for. For our vertical motion, it was a little bit different. It was accelerating downwards, so we could say constant acceleration. I'll put CA for constant acceleration. So what would that look like? Well, maybe depending on whether it was dropped or thrown up, maybe you could go sort of like this, and then like this, and then 2 dots later, and then 3 dots later, and these arrows are growing. So something like that for constant acceleration. If we're going to draw a position time graph, now it would be y instead of x, and we could have maybe a parabola or a parabola this way, depending on which way we're graphing is up and which way is down. Our velocity in the y direction, again, could look like this. If we're saying downwards is negative, we could actually also have one that looks like upwards like that, if we say that up is positive or down is positive. And one big thing here is that the slope here, it is actually closer to 9.8, but the slope is the acceleration, and we're going to say it's approximately 10 meters per second squared. So that slope being 10 is a nice friendly number for us. So in this lesson, we're not going to be worrying about horizontal motion. We're just going to be doing vertical motion. So in the future, whenever we're talking about velocity, I'm going to say Vy and things like that. So sometimes I might let it slip and just do V instead of Vy. Let's do example number 1. It says a ball is dropped from a tall building. How far did it fall after 4 seconds? So we can represent this a few ways. We can do a diagram. Okay, so well, let's just make a simple little diagram. So when you drop a ball, it falls that way. One important thing to think about is which direction shall we make as positive. Now, I think because the total motion is downwards, the acceleration is downwards, the displacement is downwards, it kind of makes sense in this example to say, hey, let's make downwards to be positive. So let's do that. Now, in our motion map, okay, check, with a positive direction, check. Let's do our motion map. So maybe we'll start here, and then we'll say, okay, it'll go 1 dot to begin with. I'm just going to use my grid here. I don't know exactly how far each grid spot is, but I can think of it in terms of seconds. So if this is t equals 0, this could be t equals 1. This would be t equals 2. And now 1, 2, 3. This is t equals 3. 1, 2, 3. And then here this would be t equals 4. Okay. When I'm talking about the motion maps, I can add some velocity in there. So if I was to do the velocity, maybe I'll pick some green for that. This is growing. So here the velocity is 0 to begin with. Here, now think again. Remember, it's accelerating at 10 meters per second every second. So to begin with, when I drop something, the word drop actually tells you in English that it's not being thrown down, it's being dropped down. So that's why the initial velocity is 0. 1 second later, well, if it's changing by 10 meters per second every second, that's another way of writing that, meters per second squared. 1 second later, it's going to be going 10 meters per second downwards. Here it's going to be going 20, and so on. Okay, I think that's lots for, actually, we got the velocity, but we didn't write the acceleration. Okay, so the acceleration, I can do another set of dots, similar dots here, just so that it's not confusing. And my acceleration is going to be the same all the time. the acceleration is 10 meters per second squared downwards. Okay, so now we can do some graphs. So the graph, now this is kind of cool in that the graph, pretty well always the velocity graph is going to be the best one to draw. So what's different about this one, we are used to seeing the graph going downwards because the acceleration is downwards, but we've just said that the downwards is positive. So when I write my velocity in the y direction versus time here, to begin with, the time equals 0, the velocity is 0, and when time is equal to 1, now the velocity is 10. So actually it's going to go up like this. Now I'll make this graph look a little better. So with this last one was 4, and then this one was 40. That's kind of cool. It goes up instead of downwards. Now I'm asked, how far did it fall after 4 seconds? I can actually solve that because the how far business is displacement. So this area here, remember on the velocity time graph, area is equal to displacement. And that's what we want to find out. So that area is equal to 1/2 multiplied by the base, which is 4 seconds, multiplied by the velocity, 40 meters per second. And notice how the units work out here because the seconds multiplied by the meters per second cancel each other out. So 1/2 of 4 is 2, 2 times 40 is 80, so I get 80 meters. That is pretty cool. Alright, so what if we did it mathematically? I'll switch to green so it doesn't get too confusing over here. So mathematically, D, I can say, well, we are doing constant acceleration, so we're going to use our big 5. So we're going to say, okay, what was the initial velocity? It was 0. What was the final velocity? It was 40. How much time went by? 4. What else do we know? The acceleration is, now careful, it's not minus 10. We said downwards is positive, so acceleration downwards is 10. I'll even put some units in here. Seconds here, meters per second squared. And what do we want to figure out? We want to figure out the displacement. Now instead of saying delta x, we're going to say delta y because it's in the vertical direction. So really we can use any equation as long as it has the delta y in it. I think equation number 1 is usually the easiest. I'm going to say delta y is equal to vi times time plus 1/2 a delta t squared. Now since this initial velocity here is 0, that means that this term is going to turn into 0. So that's nice to be able to ignore it right away. Sometimes what I do is I just put an arrow through it and put a 0 like that to indicate that's the same as 0. 1/2 times 10 over here is going to be 5 multiplied by the time, which was 4, and don't forget the squared. So is equal to 5 times 16, which is the same thing as 80 meters. Wonderful, we got the same answer. Doesn't that feel so good? Okay, so here's a your turn. It says a ball is dropped from 100 meters. How long before it hits the ground? Draw a diagram with the plus direction, draw the motion map, solve mathematically. In this case, I think the mathematical one you're going to find easier, but as a challenge I'm going to say, see if you can also solve it graphically using a velocity time graph. Okay, I want you to hit pause now. In fact, maybe what I'll do is I'll stop this video and then the next video will be the answer to the your turn. So I'll see you in a bit.